Hello again. Welcome back. Last time we were talking about population and changes of the alleles, changes in the phenotype in different populations. Today we're going to talk about Hardy-Weinberg and how we can actually measure those changes. Going to do a little bit of math. Don't worry, it can be pretty simple. I'll go through some practice problems with you as well. But Hardy-Weinberg, it's equilibrium, right? And really, Hardy-Weinberg equilibrium, to sum it up, really, there's no evolution happening. Right? You have this constant allele frequency, and the populations don't change from generation to generation. It's all, genetic variations constant. It's all fancy for just saying, hey, evolution's not happening. So Hardy-Weinberg equilibrium is necessary for this calculation that we're going to talk about. But again, the frequency of all these alleles. By frequency, and it's important to keep in mind, this is a percentage, and we can use this as a decimal or an actual percentage we want to. So really, we're talking about percentages. How many of the population have a particular allele, the homozygous, heterozygous, and whatnot. But that's what we're talking about with frequency. The conditions for Hardy-Weinberg equilibrium, not important for the calculations, but these are the assumptions that are made for any kind of equilibrium to be established. You've got to have a very large population size. You can assume infinite, but obviously that's not possible. But large, random mating, so no particular traits being selected for, choosing for over another. No mutations. Again, mutations, we've seen it all the time, right? Mutations are going to give you these new alleles and new phenotypes. So without mutations, without mutations, there'll be no change, which means no evolution. No natural selection. Obviously, if you have one gene being or allele being picked over another one, that's going to change the amount found in the population, and that's going to again lead to evolution and the change within a population. And the last one is no gene flow or migration. As we mentioned last year, sorry if you hear my kids in the background there. He just died in Zelda. No gene flow, no migration. We're not going to be introducing genes into the population. None will be leaving. Again, everything's constant, right? That leads us to the equation and the math that we'll be doing. Hardy-Weinberg equation, it's a nice little quadratic here. P squared plus 2pq plus q squared equals 1, and p plus q equals 1. Maybe it looks complicated, but it turns out it's not. If you practice this, it shouldn't be overly complicated. So p can be defined either way, but just for consistency's sake, p will be defined as the frequency of the dominant allele, right? The percentage of the dominant allele in that population. Q will then be defined as the frequency of the recessive allele in the population, again, the percentage. So if 90% of the alleles in the population were the dominant allele, it would be 0.9, and then we could figure out that the frequency of the recessive allele is 0.1. Right, 0.9 plus 0.1 equals 1. Now we're looking at this equation up here. P squared is P times P, right? And that's going to be just like the homozygous dominant, right? Two capital A's, like they're being multiplied together. So this P squared will be the frequency in the population of those that are homozygous dominant. The heterozygous individuals and the heterozygous percent in the population is indicated by the middle, 2pq, right? One dominant, one recessive allele, 2pq. Again, and if we have p being dominant, q being recessive, this is the percentage in the population that are heterozygous. And our final term, q squared, is a homozygous recessive. Two recessive alleles, q times q, or you can think of it as a times a. All right, and with that, I think we're ready to do some practice problems. All right, so we're going to do a practice problem here. So we see allele W for white wool is dominant over allele lowercase w for black wool. In the sample of 900 sheep, 891 are white and 9 are black. Estimate the allele frequencies in this sample. All right, based on the genotype, we know that the white, okay, I'm learning this technology here, it's not working so well. Let's see if I can get it here, is going to be capital W, and we know that the black is going to be lowercase w. We also think that white would also be heterozygous. All right, so in these 891 that are white, it's going to be a combination of both homozygous white and heterozygous white. The only one we know for sure are the recessive. And for these problems, really, typically you start with just the recessive alleled organisms, because that's what we know. We know for a fact that if they're black, they're going to be genotypically lowercase w. This, remember, is going to be Q squared. So now if I have frequency percentage, remember we have some part over total, so 9 in that population are black out of a total of 900. Right? That is going to give us 0.01. So I know that Q squared in that equation is 0.01, and that 1% of my population is going to be homozygous recessive or black. All right. So once I have that, right, I can get Q. This is Q squared. If I take the square root of 0.01, take the square root of Q squared, that gives me Q. Right, so that would be 0.1. So I know that in that population of 900 sheep, 10% of the alleles are going to be the black allele. Now I can figure out P, because remember P plus Q equals 1. So P is going to be 1 minus 0.1, which is going to be 0.9, or 90%. So 90% of my population is going to be the dominant allele. Once you have P, you can then figure out, of that 891, you can figure out that frequency of those that are homozygous, right? That are going to be the double capital W. In this case, 0.9 squared is 0.81. So you have 81% of the population will be homozygous dominant. And then we can figure out the heterozygous frequency of alleles, which is 2pq, which the common mistake here is you take p squared or q squared and put it in here. I'll try not to do that. That's the most common mistake I see. So it's 2 times 0.1 times 0.9, which is going to be 0.18, or 18% of the population. So you can even take these numbers, these frequencies. I know it's not asking for in the problem, but you can take these frequencies and multiply it to the totals and figure out exactly how many in that population are homozygous or heterozygous based on that. And that's the first problem. Again, these are percentages, and you often have to figure out one, if not all, of these. All right. So let me pause. All right. Let's look at our second question. A population of cats can be either black or white. The black allele, capital B, has complete dominance over the white allele, lowercase b. Given a population of 1,000 cats, 840 black and 160 white, determine the allele frequency, the frequency of individuals per genotype, and number of individuals per genotype. Why don't you pause the video now and see if you can do it on your own, and then compare your answer, and we'll go over it together. All right. Well, let's go over it. See if I can get the right brush here. So let's start with what we know, right? So we have a total population of 1,000, and we know that we have the black genotype is going to be capital B, or be heterozygous, right? And we know that the white genotype has got to be only one option, lowercase b. That means, right, for the white, we have 160 out of 1,000, which means that it's going to be 0.16, or 16% of the population. And that, remember, is going to be Q squared. All right, so that's our first answer. The frequency of homozygous recessive in the population is 0.16, and the total for that genotype is 160. If I take the square root of both sides, all right, that gives me Q equals 0.4. All right, 0.16 square root. Now to get P, right, it's 1 minus 0.4, so that P, frequency of the dominant allele in this population, is going to be 0.6. That means P squared is 0.36, which means 36% of this population will be homozygous dominant, and that will be 360 out of 1,000 will be that genotype. And 2PQ, the heterozygous individuals, is going to be 2 times 0.6 times 0.4, or 0.48. 48% of that population will be heterozygous, for a total of 480 individuals out of 1,000. And there you have it. And remember, the P and the Q, just want to last note, are the total of alleles in this population. So the total number of alleles in this population would actually be 2,000, because there's 2 for each cat. Of those 2,000, 40% are going to be recessive, and 60% will be dominant. All right, that's all I have for now. And good luck on the problems.